Okay, looks like we can start. Welcome back, everyone. We're now on double digits of weeks. We're on week number 10, so congratulations on getting here. It feels like the weeks start to go pretty fast once we get into the double digits. Also, we got through the second exam, and the grading on this is going to begin on Friday. I hope to have it completely fully graded on Friday and send the results back. But if it takes a little bit longer, I want to grade homework sets first before beginning the grading exam. I'll possibly get it done Saturday morning or Sunday evening at the very, very latest. Once everything's graded, you can see your posted grades here in the Canvas system, as well as your total grade. And I think I had another comment there, but forgot. Oh, that's right. And also be sending back your grade exam too, just like exam one. Well, for where we're at so far, we have quiz number 8 that's going to be due tomorrow. And I wrote quiz 9, but forgot to post it. So I'm going to get that posted first thing on Friday morning. It'll be based off Unit 5C, which we're working through. And we're pretty much just started right before getting into the exam last Thursday. Currently, we're on example 2 in that section. But any questions or comments at all, folks, before we get started today? Okay, well, another big announcement is we're getting closer and closer to the break. So this is not the easiest class to attend because we're so close. We're all kind of tired. We got through exam 2, but we will have class on Thursday. We'll be working in Unit 5D. After that, we'll take a well-deserved break. But for the moment, let's keep on pushing forward. Here we are in Unit 5C in Statistical Tables and Graphs. And we are working through these 3 brand new definitions, working in creating a frequency table, a relative frequency table, and a cumulative frequency. The idea here is for building a frequency table, frequency is just going to tell us the number of times certain outcomes occur according to categories that occur in the data. So we were looking into these categories where all these uppercase letters are categorized according to whether we're dealing with gas giants, Neptunian planets, super Earth planets, or terrestrial planets. And then after all the observations were made, we listed the categories: primary composition of the planets. Frequency was the number of times each one of these categories occurred in the data. So the slash marks here was just us very carefully counting. We probably can erase that at this point, so it's not as much of a distraction. Then when we went to calculate relative frequency, we're using a formula that looks very similar to a percent formula, except we're leaving it as a proportion. We didn't convert it into a percentage. As far as MyLab goes, this is the answer that they're expecting. But if you called these, say, 25% or followed the rounding and called it 30%, I wouldn't have complained too much. That's just a unit change in my opinion. The trickier definition was the cumulative frequency. But here, all we do is we find the number of data values in the category and add to it all the preceding categories. So here, there's no preceding categories above, so we just took this category, 5, added it in. For the next cumulative frequency, we took this 5, but added the prior value 5 to get to 10, and then so on, ending on a total of 20. Well, that's a refresher on what we did. We're going to build on this, looking into different kinds of data, same kind of tables, and then start building our own graphs. But any questions at all, folks, with the refresher on this one? Okay, one other thing I should mention, I was reviewing the notes before class today, and I noticed I called the data categorical data, which isn't wrong, but our book calls it a slightly different kind of classification. Let's put it maybe here, what's easier to read. Categorical data is synonymous to, our author likes to call it qualitative data. And so do many textbooks across the country, but the country's divided on this. It seems like half the textbooks call it categorical data, other half of the textbooks call it qualitative data. If you called this categorical data on the next exercise, I would know what you mean, what you meant, and that wouldn't have been a problem. As far as my lab goes, I'm going to try to stick to qualitative data when that comes up, just so that we don't get mixed up in these definitions when we're doing them as at my lab problems. So here's the definitions. Qualitative data, like in just the last problem, just consists of values that can be placed into non-numerical categories. So when we're thinking of qualitative, we're thinking of, say, the classification of those planets, or it could be something along the lines of blood types, or maybe for thinking of, say, a population of students, we could categorize them according to qualitative data belonging to whichever colleges they attend or whichever class level, freshman, sophomore, junior, and so on. Those kinds of data, because they're non-numerical, we'll call qualitative. Then the other type of data, quantitative, represents counts or measurements. In other words, when we say quantitative data, we mean numerical data. And we have to be kind of careful when we say numerical data. For a quick example, before we even look into example 2, think of this sort of situation. We have data consisting of zip codes. Zip codes are just numbers like 83409, something along those lines. But just because they're numbers doesn't mean they are a count of anything. They're not a measurement of anything, zip codes. In fact, all zip codes are trying to do is take a person and put them into categories. They're just geographical categories across USA. So data consisting of zip codes, I should not cap it there. Let's complete the sentence, is qualitative. There's an exclamation. So just because we see a number is no guarantee that it's going to be quantitative data. It has to be a count of some kind or a measurement of some kind. And if it's a measurement, a giveaway here is it'll involve some unit for sure. So those are our 2 brand new definitions to start off class today. Any questions with either one? Arguing with myself over the color coding. Let me just fix this real quick. Okay, well, example 2 is just working through the definitions. It says determine whether the following variables are qualitative or quantitative, explain why. So here's our first batch. Let's suppose we have a random sample, maybe a simple random sample or otherwise, of 450 people in Idaho, kind of referring back to that example in Unit 5A. And all we're doing this time is looking into the blood types. So there's more to blood types, but let's just say we measure along these lines, type A, B, AB, or O. What kind of data would you all say this would represent?
Qualitative data.
Yeah, absolutely. It's definitely important data. In fact, this example is not all that different than this example right here. It was just different types of planets. Here, we have different categories of blood types, and that's what we were thinking of when we say qualitative. So let's actually highlight that as well. These are non-numerical categories, and so we'll call this qualitative. We also need to explain, but the explanation for this is going to be really brief. You don't have to say a whole lot. You could say qualitative because the data is non-numerical. And really not a whole lot more to say. You could say it's qualitative because the outputs are just categorizing all of the people in the sample according to 4 different blood types. But you could also just say very briefly, non-numerical data, and that's a good giveaway. We're looking into qualitative data. Well, let's try this again. So here's some other random study that we're looking at. It doesn't mention anything about a sample, but it says the mass in grams of geological core samples, it does mention samples, it turns out, extracted from glaciers randomly selected near the town of Seward, Alaska. And that's our data. That's the whole expression, the whole the whole, sorry, having a micro sleep, the whole description of the data here. Couldn't find that word. But this one's different, right? Here, we're just saying what the mass is for each of the core samples extracted. And so a measurement is being made. We see that there's something like this, mass in grams. We're going to get numbers as our output. We don't know how many numbers. They didn't tell us how big the sample size is. But here we can say pretty briefly, this is quantitative. Since the data are numeric measurements. So far, that's pretty much how the whole set of two problems go. But now that we have two down, one interesting thought that goes along with it, let's put it in orange, is the type of data that you have also will tell us the way we give a display, the type of display we're going to use. If it's qualitative, a typical display might be something along the lines of a pie chart, or the kind of charts we'll go for in these notes would be a bar chart. So qualitative means use a bar chart. But if we have quantitative data, we don't necessarily use anything like a pie chart, certainly not, or even not a bar chart. We use a different kind of display. This would be called a histogram. So the moment we know we have quantitative data, we would display these data after we get all of the measurements of the core samples using a histogram. Well, it's in orange in parentheses, only to say that's an extra part of the problem. And we'll look into creating displays both for our qualitative data, giving a bar chart, as well as quantitative data, giving a histogram. And we'll also give a time chart as well for different data later on in the notes. Well, let's finish off these next two examples. The next one is daily amount of rainfall in millimeters measured during the monsoon season. So for this one, again, this one gave us a unit, so that's a pretty good giveaway. We're making a measurement. If we're talking about the daily amount of rainfall, then our values that we're going to get is going to be numerical for sure. So this right here is a red flag. This is, once again, quantitative data. This is a random selection of regions in Nepal where the monsoon is really, really intense. So it should be pretty impressive data in the amount of rainfall, but it's quantitative. We don't have counts on this one, but if counts came up, that would be our explanation. It's quantitative since the data, this feels redundant, but that's what it is on this case as well. Since the data are numeric measurements. Once again. Then on the last one, it says the classification of cloud types, but really the moment they said that, if we're classifying our data, it means we're throwing them into categories. So right up to that point right there, that's a red flag. It's probably qualitative data instead of quantitative. So we're classifying cloud types according to these four. There's lots of different kinds of cloud types, but we're keeping it to the four this time, it looks like, for the sake of this problem. Observed during a weather study in Canada. But here we just have categories. They looked at different clouds and they fit them into these four. Maybe those are the only four that came up during that specific weather study. But if we have a classification of data, the data looks like this. Let me also highlight that on part A just for parallelism. We can say it's qualitative now because the data we could say is non-numeric, or a different way to express this one is we can say because the data is a set of categories. So if we just see categories, like on our example one, when we're looking into the different kinds of planet types, or here, different cloud types, we're just looking at qualitative data. And if we had the raw data set, say like we did on example number one, we could put it in tables like these, and we can go even beyond that. We can start giving some graphics. Some bar charts is the main one we're going to look into. Pie charts could be given as well. But if it's quantitative, we go for something that looks like a bar chart, but we'll call it a histogram and discuss the subtle differences between the two. Well, any questions at all, folks, on the data types so far? Okay, so what we'll be doing next is doing another set of frequency, relative frequency, cumulative frequency tables. Then we're going to launch into creating our own graphics by hand, which is quite a tedious little task in its own, but it's a good way to really understand what is a bar chart, how to read it, interpret it. Similar for a histogram, probably the best way to really develop that skill is to do it ourselves. So we're going to make our own graphs. Then when we go into Unit 5D, we'll look into pre-made graphs, analyze what information we see there. Here's where the graphs start to get a little bit more fancy, stuff we wouldn't want to do by hand. So we're going to think of Unit 5C as just skill building to get into that unit. So first, we're going to turn around the data. Example one was qualitative data, but now example three, we have something that looks numeric, so it's probably quantitative. But you really can't tell just by looking at the data. For example, zip codes are not quantitative, they're qualitative, putting people in geographical categories. So let's read through the data to see if this really is quantitative data, numerical data. It says here, to start off the context, while some decorative sunflowers can tower to 10 to 15 feet, heights of 150 to 165 centimeters are very typical for agricultural commercial sunflowers. So if some agricultural commercial operations trying to, say, grow sunflowers in mass for the seeds or the seed oil, then they actually want them not 10 to 15 feet high. They're going for these heights, 150 to 165 centimeters. Already, that's kind of a unit analysis kind of problem. We can convert these into feet, but I did the conversion here right in parentheses so we don't get sidetracked in a whole nother chapter 2 topic. 160 centimeters is about 5.25 feet. So it says next, commercial varieties are specifically bred to be shorter, have thicker stalks to prevent what they call in this industry lodging, which is their way of saying falling over in the wind. If you ever grown these impressive sunflowers, that's one bad windstorm like we had just last week, means they're all possibly wiped out, which is kind of frustrating when that happens. So with commercial sunflowers, they grow them smaller, around 5.25 foot, bigger stalks so they don't fall over. And also because if they're going to harvest them, if they're uniformly sized, then it's easy to harvest the seeds through mechanical combine harvesting. So this is the overall context of the problem. And now we have data. It's looking like this is more and more quantitative, but if they're measurements, we want a unit. So let's keep on reading. Well, now it's saying for the instructions, use 5-point bins to make a frequency table for the heights in centimeters for mature sunflowers in a botanical study. So in this study, they're probably going for, again, trying to get a breed of sunflower all at about the same height. And in this study, it says we have measurements in centimeters, and here's all these measurements. So we want to, once again, do a frequency table. Also, we're going to look into relative frequency and cumulative frequency at the same time. And just to tie in the last example, now that we know that these are measurements, the height of the sunflowers in centimeters for this study, this is now quantitative data. So the first step in getting to our fancy displays, whether it's going to be a bar chart or a histogram for quantitative data, is we would need a frequency table. Relative frequency and cumulative frequency we're doing just for the sake of review, but let's begin. It says use 5-point bins, so that's something that's new here. For doing a frequency table, it's different from example 1. We don't have categories, but we can force a category, even in quantitative data, using these so-called bins. First, before we even get started with the 5-point bins, the best way to start organizing these data is to look for the minimum value we see here, as well as the maximum value. So let's make that our step 1 in the process. The minimum value, the smallest measurement we see here is, and let me know if I'm missing one, I see 152 as a minimum, and next is 151. Let me circle that temporarily. I think that's the minimum, 151 centimeters. Maybe that one didn't get very much sunlight during the experiment by just chance alone where it was planted. So now that we have a minimum, it's probably good enough to get us started, but let's look for the max as well. The max is, I see a 161, 165. That's probably going to beat out everyone else. And yeah, unless I missed something, let me know if I missed a value. Looks like the maximum is 165 centimeters. Well, knowing we're using 5-point bins, that's going to be the width of every category in centimeters, and the minimum, that's enough for us to get started. We'll build a frequency table, the relative and the cumulative, and again, those are the things we need to get a good display of this, build a histogram. Any questions first before we get started? Okay, well, let's begin by putting down the table. For doing this as a MyLab problem, the table is already set with one column already put in, so it's a bit easier in MyLab. So think of MyLab as kind of the warm-up problem. This is the slightly more challenging problem that we're doing in the notes. That could be a quiz problem, an exam problem, because we're building the tables ourselves. So we'll definitely practice this when we review for exam 3 as well. So I'm going to throw down several rows. We'll put down some more in case we need more, but let's start with this so far for the table. And if you're using Microsoft Word, you could just build out the table, but that seems unfair if you're possibly doing this as an exam question by hand. We're pretending now that this is a true exam question. So first in column 1, if we were thinking of what we did in example 1, we put the categories here, but this time we don't have natural categorical data. We're going to be using bins. So let's just put in what the variable is right in this description right here. So this is going to be height in centimeters. I'll abbreviate it to just cm for centimeters. And if we're doing 5-point bins, you really have a lot of choices that you can make on this. In MyLab, these are already printed for us, so there's no choice to make. Some people might start at 150, which is completely fine on a quiz or exam. That's going to be a great way to start. Other people might start at 151, and that's completely fine as well. I'll leave it up to you where you want to start. Let's say we start at the minimum value. That means this category is going to go from 151 centimeters to, well, if we're doing 5-point bins, this is 1 point already, 151, 152, 3, 4, 5. We end at 155. So now this is the 5-point bins being expressed in that category. Then we just move on to the next category. We have 155 here. We start at 156 centimeters next. Then because it's 5-point bins, here's where we go 56, 7, 8, 9, 60. That's 5 points. So up to 160 centimeters. And then on it goes. It's kind of tricky in a certain sense. Does that make sense to folks on how we're building these categories? Okay, again, for me, what makes these tricky is an easy mistake to make is to go 150 to 155. If you did do that, then I wouldn't be super picky on a quiz or exam problem, but it's not quite the intention of what they mean by 5-point bins, because this would include 6 different possible outcomes rather than just the 5 if we go 151 to 155. But again, if you made the categories slightly off, if you went to 150 to 155 on an exam 3 question, you'll have a different number here on the next column, but as long as it fits with the category you constructed, I wouldn't take off points. I wouldn't be super picky. Let's keep on going. It's nice to have the maximum value here because it tells us we need more rows. So we go off to the next 161 to 165. We don't need to say the unit each time because the category header here mentions it. This actually gets us to the maximum, so that does the job. Looks like we just need these 3 rows right here to capture all the data. Let's put in one more row that just says total. This will be like a built-in check as we go to the next categories. And by the way, did it tell us how many observations we made? It did not. Let's count them out carefully. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, unless I miscounted. So there is n equals 20 observations altogether, where this n is referring to as the sample size or just number of observations. So we're expecting 20 when we go to build this column. And this column we're building here is going to be frequency. So again, we're not doing anything too fundamentally different than what we did in example 1 with those exoplanets. The major difference is the data is now quantitative, so it has a different feel in this column. But even quantitative data, you can force in categories, and this is how we were doing it by that requirement there, 5-point bins. Now, this is the tedious end where we have to be really careful at this point. When we said our first category goes from 151 to 155, we need to count that out really carefully. Doing this in MyLab is tedious, so going slow is going fast for MyLab on a problem like this one. So let me count them out carefully. Here's 1, I'll use tick marks here. Then 2. Off to here, we have the 3rd one. Then all the way down to, just double checking I didn't miss one. I did miss one. Here's the 4th one. 155 is included in that category. And then further to the right, they're mostly increasing, but there's some smaller ones. 153, 155 again, and 156 is on the next category. So I counted 6 altogether. If you left tick marks here on a quiz or exam question, that would make sense. It'd be kind of understandable because it's a tricky problem. But for MyLab, it wants a number, so we have to put 6. Well, does that make sense to folks so far on that one? Okay, let's go on to the next one. I'm going to use a different color just so that I make sure I don't mix up the categories. We can't let any of the observations in the quantitative data be double counted. So next, we're going up to 160 from 156. So we skip the first one. Here's 1 observation. Then 165 is skipped. 163 is skipped. We include 160. 157. 156 barely makes it in. 159 makes it. So we skip 162, 164. 158 is in that category. 160 barely makes it in. And 156 is there as well. So I'm counting 7, but it's kind of tedious once again doing this visually and manually. It's easy to get lost. A lot of data to look at. Let me know if you're getting a different number. So I've got 7 altogether, expecting a total of 20. That implies If no mistakes are made, there should be 7 in this category as well. But that's where we get to double check this. The ones we didn't tick off should be 7 altogether. Oh, Amy says 8 were counted. Let me double check my data. So I missed one somewhere to get the 180. I'm going from 156 to 160. So I would include, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's 8 altogether. I got them slashed off right, but I think I just lost track down here, putting down the tick marks. Thanks for mentioning that, Amy. 8 altogether on this one. That makes a big difference in the problem. Because now this should add up to 20, so we should have a 6 here altogether to make that 20. So let's double check again. If that's really a 6, we should have 1, 2, 3, 4, 5, 6 observations not slashed off just yet. And now with that correction there, thanks again, that does come out right. 6 unmarked values. So it's kind of tedious, but once you get through that part, the rest of the problem flows a little bit faster. Let me go back to blue just so that's all blue for frequency. Here's the data all marked up. That's probably how it might look on an exam setting, depending on how you do it. I'm going to reset that so it's not a huge visual distraction. And now we're on to the next thing, relative frequency. But so far for the data set, we can answer a lot of questions about it. It looks like most observations are between 156 and 160 centimeters, and it's pretty symmetric. 6 more in this range, 6 more on the higher up range. Remember, for this context, being too small or too high are both problematic. They probably want them all to be within a certain value. So these would be possibly the ideal sunflowers in the set. And the experiment would go better if they could get a genetic variety where more go into one category, less on the fringes like we see here. But that's how the data fell for this experiment. Next thing we'll look into is relative frequency. Here, the thought is we're thinking in terms of percentages or proportions. And you can give me either when you're doing these as quiz problems or exam problems. But relative frequency is, by definition, a proportion. And so that's the number that's expected as a WebAssign, or excuse me, a MyLab type of problem. Sorry, WebAssign is a different class. I get them mixed up. So all we're doing for these is we're going into the calculator. We're taking the frequency we see on the left, divide by the total, 20. If you multiply this by 100, you're converting it to a percentage. But for the homework, it has to be exactly that value. We're rounding to 1 decimal place, so no rounding on this one. We're getting a 0.3. Then if we did it again on the third row down here, it's the same numerator, 6 divided by 20, so that's a freebie. We get 0.3 once again. And the total for relative frequency, if these were percentages and we didn't round, the total should be exactly 100%. But as our proportion, we divide by 100, so the total should be exactly a 1. That means this one should be 0.4 without throwing it into the calculator, but we'll still do it. If we made a mistake anywhere, we're going to spot it right here. So 8 divided by 20 does give us the 0.4. So that gives us good confidence that we're on the right track with the relative frequency. Last one's cumulative frequency, but any questions at all, folks, on that column there? Okay, well, let's practice this last one. Cumulative frequency, if we're going to build that out. Let me fix the penmanship there. Okay, now if we're going to build out cumulative frequency, the thought is we're not looking at the relative frequency column. We're looking at the frequency and just accumulating the values as we go down the rows. But there's a nice trick on cumulative frequency. The very last row is where the total would come up. And down here, total is nonsensical, so we would leave this cell blank in this spot. No one would stop you for adding up everything here, but the value you get wouldn't make any direct sense on the problem, its context, or any of the data. So we usually leave this blank. So here's how cumulative frequency starts. In this cell here, we just look directly to the left, grab the value and write it in. Then when we come down a row, we're taking the value 8 and we're adding all the values directly above. So we're taking 8 plus 6 to get 14. Then when we're here, let's suppose we didn't put in 20. What we would be doing is taking the value to the left, but adding the preceding categories, which would just boil down to 6 plus 14. It comes out as a 20 as a double check that the cumulative frequency table is correct. So the table is a lot shorter than we did on example 1. Example 1 had quite a few more rows, I think, well, 5 rows about. But the tough one on these data were actually binning them correctly, getting the frequency in. I miscounted on 7. That's an easy mistake to make. But also building out the categories themselves can be tricky when we're doing this by hand. Well, we did it, folks. That's our now frequency, relative, and cumulative frequency table for quantitative data. But any questions about it? Okay, the purpose for all these tables that we're building is if this study is really important, people are going to make financial decisions based on the outcome of the study. And the botanists who did this study just give people making all the decision makings this data. That's definitely not good enough, right? We have to kind of understand the data better, and looking at a cloud of numbers is kind of dizzying. And if it's qualitative, looking at a cloud of categories, it's not too informative. The very first step to taking raw data like this is put it in a table. This is telling us the distribution of that categorical data, or qualitative data is the way we'll typically say it. And if it's quantitative, it's hard to make heads or tails of this, but once it's been displayed here, we're looking at the distribution of data through the frequency or the other columns, we can see a lot more clearly what's going on with the data. The fact that it's pretty symmetric, that it's accumulating mostly in this one range right here, is quite informative. Then it's still not good enough. If these studies are really important, the next thing we want to do is create graphics based upon them. So that's what we're going to turn over to looking into now: bar charts and histograms for qualitative data and histograms for the quantitative data. So let's take a look at how those go. There's some guidance that the author gives us in building these graphs. If we're doing them in MyLab doesn't allow us a structure to actually hand draw a graph and build it. But these are multiple choice, and so this is some guidance that you should look into. Sometimes you can see a graph that looks like it's about right, but something's messed up. Maybe the title's wrong, or the scale is incorrect, or something along the lines of the unit's wrong on one of the scales. It could be an issue. So let me fix this grammatical thing right here. Hang on, let's get rid of that. That's kind of a weird visual distraction. Let's go to proofing. And that option, let's take that away so we can not worry about any weird anomalies there on the grammar. So here's our new example 4. It says the accompanying data gives the number of confirmed moons for the 5 major outer planets of our solar system. Make a bar graph for these data with the bars in descending order. And here are the planets: Saturn, Jupiter, Uranus, Neptune, and Mars. Well, already you might have spotted something kind of weird about these data. The number of moons is substantial for a lot of these outer planets, but one of them is kind of off a little bit. Let me get rid of that period. Mars just has two, and this was supposed to be outer planets. I think a lot of people would agree Mars is usually not considered to be an outer planet. Usually we're thinking beyond Mars. Somehow it made it into the data. It's going to make our graph look a little bit weird, but let's keep going with it. So we'll see what happens with this data if we include something that probably doesn't belong. First thing to notice is this data, even though it's giving us numbers, this is not quantitative data. This is qualitative. Essentially, what's happened with this data is, hang on. No, I think I got confused on this. Looking into this data a little bit more carefully and our definitions, I was thinking qualitative in some weird sense, but Saturn telling us we have a count of 146 moons, Jupiter 95 moons, and so on down the line, tells us by those definitions above, this is quantitative. Probably didn't drink enough coffee today. Sorry about the distraction on this one. This is quantitative. Because these are counts. They're not measurements like we saw in the example 2 for quantitative, but this is our first set of quantitative data that are just bona fide counts. 4 different planets altogether. Okay. Hang on, kind of getting mixed up on what I said earlier. Gives a number of confirmed moons for 5 major outer planets of our solar system. Make a bar graph for these data with bars in descending order. Kind of debating myself on this one. This is a tricky set of problems and definitions as well. Let's go back to these original definitions and think about the data one more time. The reason this is an important one to think about is, remember at the very top, we did make one statement that if it's qualitative, we'll use a bar chart. If it's quantitative, we'll use a histogram, and we're definitely not mixing that up. So we need to make heads or tails of that data. It did say to make a bar chart, which conveys something very specific about these data. So here are the definitions. Now, once again, let me backtrack on this. I'm debating myself a little bit on this problem right here. We have 5 different planets, and altogether, quite a few moons. Let's put them all together. So there are 146 plus 95 plus 28 plus 16 plus 2 moons that we're taking a look into. So there are 287 observations altogether, 287 moons. And we're doing something with these moons. They are, well, they're being categorized in fact, right? Some of the moons belong to Saturn, some to Mars, some to Neptune, and so on. So maybe the best way to think about these 2 definitions, again, these can get pretty tricky. This one kind of put me through a loop, is another way to think of whether it's definitely qualitative versus definitely quantitative is, what are we doing with the data specifically? Sure, we have counts here for each of the planets, but you know what? We had counts here as well when we looked into the frequency for all of these categories. So just because we see counts doesn't mean the data is quantitative whatsoever. What we're really doing with the data, oops, that was a little too far, which was 287 moons, is we categorize them according to which planet they belong to in the very first place. So 287 moons categorized by their planet they belong to. I'll just say briefly their planet. This means the data is qualitative. but definitely confusing. I had to debate myself a little bit on that one. Sorry about the distraction for just starting off this problem. It's qualitative, which means the problem saying make a bar chart or bar graph of these data will make sense. The bar chart goes along with qualitative data, like we mentioned in our earlier comment on example 2. Well, any questions or comments, folks, on just the determination of what kind of data it is before we get started? Okay, now that we have a good sense of what kind of data it is, what kind of graph we're going for, let's look into the guidance on creating this display. Our author says, this is typed out verbatim from our textbook, first thing we should create is a title or caption that should explain what we're looking at when we see this bar chart. What is this information all about? The source of data, if applicable, they say, but here I don't have a data source, so here's what we're going to call this. This is just going to be the moons of 5 major outer planets. If you just said outer planets, that would be fine as well. I'll go for the brief title, moons of outer planets. So that's going to be our graph title on this. And I'm not going to be too picky. You can make some other title as long as it fits in with the context of the data. It'll work out just fine. Next, we're going to have a vertical scale and a horizontal scale. So we might as well just start there for our second step. Here's the vertical scale going this way. Horizontal scale going this way. For the vertical, what we're placing here is the frequency. Which is the number of times a moon came up for each one of these different categories. For the horizontal scale, the categories will be displayed, and that's going to be the categories of these 5 different planets. We don't want to put them all at once. We're going to put them in carefully. We'll put in a bar that corresponds to the height of the frequency that's labeled here for the data. So we'll say frequency here. That's going to be our vertical scale. We should have numbers going along the vertical axis as well, indicating the scale in our graph. The numbers should line up with the tick marks. The marks along the axis that precisely locate numerical values. So before we get started on that, let's look into just what kind of data we have. Our data ranges from a minimum value of 2 and goes up to a maximum value of 146. In our display, we're going to give a pretty honest graph, so we're definitely going to start it at 0, but we probably would have already with a minimum value of 2. We're going up to 146, so you have a lot of choices you can make here. You could go up by, say, tens. That could be a lot of counting, up to 15 different values. You could go by 20s or 25s, that might be appropriate. But probably don't go by 50s and making just a few tick marks altogether. We want some fine granularity, but it's really going to be kind of up to you. These are kind of tricky problems because there's a lot of choices you have to make. I would say try to avoid going by ones, definitely. You don't want to count out 146 tick marks. Don't go by 5s, don't go by 50s, find a happy middle ground. And I would say for these data, probably 25 is about right. So if we count this off by 25s, here's what the vertical axis would look like. We're going from 25, 50, 75, 100, 125 to 150. So try to do the best as you can to try to make an equal spacing between every one of those tick marks. Also, make sure that the minimum value is within the tick marks, as well as the maximum value. So we didn't start off at 125 because we have to go up to the very next one to include the 146. So we have a vertical scale. There's no 150, but this is going to tell us about relatively where the 146 is going to land. Any questions on getting the vertical scale down? Okay, now we're nearly ready to build the graph. Some of you might have already built it out already. For the rest of it, we're focusing on the horizontal scale, so we're going to be using the categories for the qualitative data itself. The guidance says categories should be indicated along horizontal axis. Tick marks are not necessary for qualitative data, which we do have after a bit of a debate. Sorry about the distraction on that. It says include an axis title that describes a variable that the categories represent. And I would say that's kind of optional because once we put down the categories, it's pretty clear we're talking about planets. But if you're doing this as a MyLab problem and you're following this to the letter, it wouldn't be a bad idea to add a axis title here as well. So let's call this the 5 major outer planets. Now, finally, it says make a bar graph with the bars in descending order. The data is given in a descending order, so it's kind of friendly for that. Start with Saturn. For Saturn, we have a frequency of 146, so it's going to be at a height just shy of 150. And we're doing this freehand, so it doesn't have to be perfect. If you went slightly higher, slightly lower, but you're in the right neighborhood, then you're going to get full credit. So I'm not going to take out a ruler or anything like that, and you're not required to bring a ruler to exam to get this perfectly. If the height was, say, way down here or way high here, that's when you could lose a point. But if it's in the right relative neighborhood of about 146, according to your y-axis scale, then that would be an acceptable bar. You might shade it, but you don't have to get too carried away. And if you didn't shade it, that's okay as well. So that's one down. It's called a bar graph or a bar chart, and that's just our first bar. Next, we need a category for Jupiter. We'll place this here. Trying to write these diagonally to fit them all in. So Jupiter goes up to 95, so just shy of a frequency of 100. So I'll place a tick mark about there. To my eye, that might not be perfect, but it'll do the job. Another thing that we're trying to do is try to make the widths about the same. If the area is a little bit off because I made the width a little bit bigger, that actually can deceive our eyes into thinking Jupiter is a major category when it really isn't. So if we went like this, we might lose credit. It can't be that extreme. But if you're doing this freehand and it looks about like the one I started off with, may not be perfect, but it's about right. I'm not going to be picky when you're drawing these freehand. So that's the next category, Jupiter. Then we just keep on going. The next one's Uranus. This one is at a height of just 28 moons. I mean, that's a lot based off being a person on Earth, but on the graph, that's starting to get kind of low. Here we have 25, so 28. I'm just going to try to make it slightly higher. That'll do the job. And if it was slightly below when it's on paper, it's in the right ballpark. So I'm not, again, going to be super picky for a by hand sketch. Now here's where it gets a little bit tougher. Neptune only has 16 planets. So here, that's halfway 25, so that's about 12.5. But we're going for 16, so I'll make it slightly higher. It gets really challenging to get this down perfectly, so don't worry if it's not exact. It just has to be a little bit lower than Uranus. So here's the 16. Then one last one, Mars. And now it gets really challenging. Mars starts to look like it's possibly a miscategorization in a certain sense. When we put Mars down, we're at a height of 2, right? So that's just barely above 0 here on the axis. So this one's the most challenging one of all to plot. you go like this and just kind of scribble a little to kind of emphasize there's a bar here, but its height is so minimal, you can't really see it. We're just sort of emphasizing it this way. That would do the job. And, really the height of this one might kind of convey it's like 4 or 5 really, but I won't be picky again. This is a by hand sketch. And here's the moons of the outer planets. The data was already put into a frequency, not as a table, but it was listing out the frequencies. If we had the data that looked exactly like these, we would have had 287 different listings for each one of those planets the moon belonged to. So that would have been overwhelming, but the frequency was already done for us. It was listed out in these numbers in blue. And so we could just jump right to the bar graph immediately on this one. So those frequency tables we're building, that's really just kind of the first step in building these kinds of graphs. This one didn't have any follow-up questions, but some of them will. Here, it was just majorly the skill of building the graph in and of itself. Well, any questions at all, folks, on building this graph here? Okay, well, let's try out another one. If we can do this for qualitative data and get a bar chart, or again, this what is called a bar graph, then we can do it again for quantitative data, but we change the type of graph into a so-called histogram. So our data is a little bit different. We have to make artificial categories inside the data itself, but once we do that, we can build the histogram that goes along with the data. So here's the context we're going to give that a try. We're going to keep these ideas in mind as we build our next graphs. This one has already done the work of building out the frequency table for us. So here we have the bins. It looks like they're at width 10. So width 10 bins. This column here is the frequency, number of trees. And so it looks like based off this seasonal yield in kilograms, now it's definitely a measurement. It has a unit. This data is quantitative, which means for this quantitative data, we'll use a histogram. So same kind of problem, just different data type. Before we just launch into the histogram, it's helpful to know what's going on with this data, especially since there's a follow-up question on this one. Let me highlight this in yellow just so I don't forget we have to answer that direct question as well at the end. So here's the new statistical context. It says a soil amendment. That's kind of a funny word, but let's run with this definition. A soil amendment is any kind of material added to soil to improve its physical properties and create a better environment for plants to grow. So fertilizers are added specifically to feed the plant by providing nutrients. Soil amendments are added to fix the soil itself. So this part of the context is saying, when we say soil amendments, we're not thinking of adding Miracle-Gro necessarily. We're trying to put something into the soil itself to help the plant. They alter the soil's structure to improve water retention, permeability of the roots, drainage, which some plants require great drainage, some plants require less drainage, and aeration. So that's the start of the context. We're thinking about soil amendments, stuff we're putting into the soil. They can be organic or inorganic. And the actual study says a team of agricultural scientists is studying the effects of a new organic soil amendment on the fruit yield of heritage green gauge plum trees. That's a great plum. At the end of the harvest season, the researchers carefully weight the total usable fruit produced by each tree in a large test orchard. Use a provide frequency table of the seasonal yields in kilograms from these plum trees to construct a corresponding histogram. So that's a setup of the problem so far. I wish the context went a little bit further now that we're reading this. It never said what the new organic soil amendment even was, but it's organic, so it could be something along the lines of peat moss. Possibly. Or maybe a compost of some kind, who knows? But it's some kind of thing we're adding to the soil, mixing into the soil. Then they planted a large test orchard of these plum trees and measured the seasonal yield in kilograms. So this is the quantitative variable here. And this right here is the binning of something along these lines. It's much like taking these numbers right here, which were heights in centimeters, dropping them into a bin just like this. We're just looking at one column, frequency rather than relative frequency. So that's this column right here, number of trees. And from this, we can now produce a histogram next. Well, any questions at all, folks, on the context so far? Okay, so first, let's just drop down some axes. Here's the vertical axis going this way, horizontal axis going this way. And on this horizontal axis, here, this is going to be the variable itself, the seasonal yield. In the prior problem, it was the categories, the actual planets. But for the quantitative variable, we forced in arbitrary categories with bins at width 10. We could have done different widths and it would have been a different graph. So that's also an interesting thought about the histogram. The actual graph you get is highly dependent on the categories, which is based upon the bin width. We don't want that width too small because then it's going to look like a sawtooth pattern. We don't want it too big because then there's just going to be one bar in this display. But there's some carryover from what we did before. Going this way is going to be frequency. So we don't need to say any more about that unit title. Frequency is just number of observations that fell into certain ranges. We have a minimum value of 1, a maximum value of 14. So I'd say this time you could count off 1 through 14. That would be just fine. Probably don't want to go by fives. That's a little too blunt. It's going to be harder to estimate the heights. I'd say a happy middle ground might be go by twos. So we can say for our tick marks, we'll go 2, 4, 6, 8, 10, 12, and 14. And again, there's no necessarily wrong answer here unless you went by, say, tens, and then our graph would be a little bit funny. If you went by ones, that'd be fine. If you went by threes, and even fives would be okay. That's just a little bit more challenging if you did go by fives. So try to make the work a little bit easier by making this granular enough, not too blunt, and make sure you're just not counting off too many tick marks. If it feels off like you're counting off 20 different tick marks, maybe make them a little bit more larger so that you're not doing as much work. So we have frequency going this way. We haven't thought of a title yet, but we can come up with one. Echo says, are the vertical and horizontal lines always supposed to be even lengths? No, not necessarily. So these could have been any number. You could have gone by threes and fives, and that would have been just fine as well. I think I went for evens because it's just a little bit easier working with round numbers. Here, this was odds and evens. And twos just kind of seemed to make sense. It was a good number of tick marks. And also, it seemed to fall with the data a little bit nicely. We're getting even values for almost all the data observations. Other questions at the moment? Okay, so we have frequency for the vertical axis. On the bar chart for the horizontal axis, it was the categories. Here we have imposed categories, so we're not doing anything too different. We'll just say that this is seasonal yield. In kilograms. So we have a title, it tells us exactly what the unit is. And maybe for an overall graph title, we can call this, let's say, yield of green gauge plum trees under a soil amendment. Again, that's kind of an interesting word. We're amending the soil, fixing it essentially, making it favorable to this specific tree. So that's pretty much our setup. Next thing we're going to do is use these bins, represent them on this horizontal axis, and then start using the frequency to build the rest of the histogram. One thing that's a little bit interesting here is, notice how these are binned at width 50. We don't necessarily say that this is the origin, that we're starting at 0. We would probably say that this is 50. We're going with bins at width 10, the next tick mark. This time it is tick marks on the horizontal axis as well, is 60, then 70, 80, 90, and let me make sure this goes long enough. Try to make them equal width to the best of your ability. Here's 100. And finally, 110 for the final tick mark. Now, what we're doing is essentially putting in the bars next. But what makes this a histogram and not a bar graph is the width between the bars. That's really the only thing that's different. For a bar graph, because we're doing categorical data, we almost always put a distance between each of the categories. But with quantitative data, these are a little bit different. There's an inherent ordering of the number line already, and so there's no gaps between one and the next. They flow continuously across all of the categories. And that's really the only difference of what makes this a histogram as opposed to a bar graph, like in the prior problem. Well, we have just a couple minutes and some change before we're out of time. I don't want to rush through this question right here. So we'll come back to this one when we come back on Thursday's class. Move into the next problem, putting down a time chart on this one, this graph slightly different than the others. And then we'll move into the next unit on looking into some graphs that are already pre-made. And our goal is just to look into the context and understand, say, some comments about the graph or some computations relative to it. But any last questions or thoughts, folks, before we call it a day today? Okay, well, have a great night, folks. If you created this graph already, then good on you. We'll come back on Thursday's class, the last one before the break, but I'll definitely be here. Finish these off and then work into the next section. But have a great night, folks. I'll get that quiz posted first thing on Thursday morning too, if you'd like to get started on it. It's doing these kind of graphs like we were doing here as well as class. But have a great night. I'll see you all Thursday.